Hi, this is Rick Kolk, and today I'm going to discuss the VisSim embedded high-speed interactive data exchange for data transfer from the target to the host. Specifically, we'll discuss the following topics: using the monitor buffer to record high-speed data from the target, configuring the plot blocks to display the monitor buffer contents in an oscilloscope-like manner, displaying the target percent CPU usage, and controlling the target update time. The JTAG interface between the host and the target, circled in this photo, communicates data at approximately 100 Hz. The JTAG communication rate is often very slow compared with the execution rate of the target, which is often in the kilohertz range. The monitor buffer read and the monitor buffer write blocks, located under the Embedded Piccolo menu, provide a mechanism for a debug model to do the following. Number 1, buffer a large volume of high-frequency data acquired on the target. 2, transmit the data periodically over the slower JTAG interface from the target to the host. And 3, make the buffer contents available for display as a vector of data at semi-regular intervals on the host. The monitor buffer sequence of operation is described in this slide. The target's operating at a 10 kHz update rate. On the target side, a monitor buffer write block, shown here, is connected to the target data compound block, shown here, and configured with buffer size equal to 1001 elements and buffer ID equal to 0. The monitor buffer write trigger input, named trig1616, shown here, is controlled by a pulse train block configured with time between pulses set to 0.01 seconds. On the host side, a monitor buffer read block is added and paired with the monitor buffer write on the target by setting its ID buffer to 0. Notice that the buffer size is the value specified in the monitor buffer write and non-editable in the monitor buffer read. The monitor buffer read is connected to a plot block configured with its external trigger being activated by the trig output of the monitor buffer read. The monitor buffer operates as follows. First, the monitor buffer write 0 begins recording a new buffer of data when two conditions are met. First, trig 16,16 is 1. Second, the buffer is empty. Recording will continue uninterrupted until the buffer is full. Second, when the buffer is full, the monitor buffer read 0 trig output will produce a 1 pulse. The plot block connected with the external trigger receives this trig output and displays the monitor buffer as a vector of data, and then the buffer is emptied and ready to accept new data. Multiple monitor buffer write and read blocks can be added to any diagram. However, as additional blocks are added, the real-time performance will degrade. The VisSim Diagrams Toolbox Fixed Point menu contains many useful blocks for embedded applications. The variable frequency RAM32 block, located here at the bottom, is particularly useful in creating a repeating time signal. To illustrate the behavior of the RAM32 block, we will apply a 10 Hz input to it. We will select a range of 0 to 1 and set the simulation to run for 1 second in increments of a millisecond. Executing this, we see the sawtooth signal evolve, and 10 cycles are displayed in 1 second. If I reduce the input frequency from 10 to 5 Hz and resimulate, we see 5 cycles occurring in the 1 second period. This example illustrates the use of the monitor buffer to produce an oscilloscope-like display of a sine wave signal generated on the target. 3 important blocks are used in this example. The variable frequency RAM32 block, located under Diagrams Toolbox Fixed Point, is used to create a repeating time waveform, which in turn is used to create the sine wave. The monitor buffer write block, located under Embedded Piccolo, is used to record the sine wave time history. And finally, the monitor buffer empty block, also located under Embedded Piccolo, is used to trigger the monitor buffer write when the buffer is full. The following naming convention is used for the source and debug models. Let's get started and build our source model. First, we need to add the configuration block located under Embedded Piccolo F28 config. I'll place it on the screen, make sure the CPU is selected correctly, internal oscillator, and the JTAG connection. Next, we'll use a slider located under Block Signal Producer to create our frequency input. I will set the slider lower bound to 50 Hz and the upper bound to 500 Hz. Next, we'll create our sine wave signal using a variable frequency ramp 32 block configured to range from 0 to 1, connected to our frequency input with its output scaled to radians by using a gain block set to 2 times pi and processed by a transcendental block sine to produce an output that I'll record in the variable y. Before continuing, let's simulate to make sure that our model behaves correctly. I will, under System Properties, set our time step to be 0.1 milliseconds with an end time of 0.1 seconds, and I will attach a plot block to the y output. I will set the frequency to 50 Hz and simulate this. And in 0.1 seconds, we have 1, 2, 3, 4, 5 cycles, which is correct. Let's increase this to 100, and we see 10 cycles. And 200, we see 20 cycles. So at this point, the sine wave has been modeled correctly. Let's create our target calculation compound block, naming it Target Calculations. Now I'll go inside the target calculation block and add our monitor buffers, Embedded Piccolo, monitor buffer right. So for monitor buffer right 0, we will configure it with a 250 element size and set the ID to 0. For our second monitor buffer, I'll copy and paste this. We'll set the ID to buffer 1 and assign a value of 100 to the buffer size. In right 0, we are going to trigger this with an Embedded Piccolo monitor buffer empty block. To improve performance, instead of feeding the Y signal directly into the monitor buffer, we will convert it to fixed point by using a convert block located under the blocks menu, fixed point, convert. And we will convert Y to a scaled integer with a radix point of 8 and a word size of 16. Connect this up. For the second monitor buffer, we are going to trigger this buffer based on the sine wave rising through 0 from a negative to positive value. We will need a cross detect block located under nonlinear, cross detect. We'll set the detect point to 0. And because we would like to trigger only based on the negative to positive, we will limit this output with a limiter to pass only the positive pulse. So I'll set the lower bound to 0 and the upper bound to 1. And we'll also convert this, adding labels to make the diagram more readable and straightening the wires. I've also added a square wave triggering the blue LED on the board, which is on channel 39, as a heartbeat. And also labeling the input frequency as a variable and feeding that in turn into the variable frequency ramp 32 block. My compound block is complete. So let me move up a level, and we will generate code by selecting the compound block, Tools, Code Gen, Include VisSim Communication Interface, Compile, and our out file has been created. We'll now create the debug model by saving our source model with a name slightly modified to include the -D at the end of the name. Having done that, I will delete the target calculations block and replace it with a Piccolo target interface block. And I will configure the target interface with the out file that I just created from the source file. I'm going to make sure the target interface block is configured to show the CPU utilization by checking this block. And I will record the CPU utilization using a display block, which I'll attach to the output pin of the target interface. Next, we need the monitor buffer read blocks located under Embedded, Piccolo, Monitor Buffer Read. And we're going to need two of these. So the first one I'm going to set up to be paired with buffer ID 0, and the second paired with buffer ID 1. I'm going to capture their outputs in a externally triggered plot box. So I'll go to Signal Consumer, Plot, External Trigger, and hit OK. Now we'll set the range of the plot box according to the number of elements in the buffers. In the top buffer, ID 0, I'm recording 250 elements, and I'm running this at a 10 kilohertz rate, which is a 0.1 millisecond, which means that I'll have a time range spanning from 0 to 0.025 seconds, which I've set in the plot on the X upper and lower bounds. In the second monitor buffer, I'm recording 100 elements, again at 0.1 milliseconds, meaning the range will go from 0 to 0.01, which is set in a similar way. We will now run the debug model on the Launchpad, and we will view the monitor buffer outputs. The upper monitor buffer is triggered when the 250 element buffer is full. The lower monitor buffer is triggered when the sine wave being recorded crosses 0, going from minus to plus. The target interface block is configured to run at 10 kHz based on the original diagram, and we've selected Show CPU Utilization, which will allow us to see the % CPU used at the various sample rates. We'll begin by running this model at 50 Hz. Click and go. We can see the out file being downloaded to our target. The target begins operating, and we can see it's alive with the blue LED flashing at the 1 Hz rate. At 50 Hz, the upper plot is displaying about 1.5 cycles of the sine wave and 250 elements. In the bottom monitor buffer, we're seeing half the cycle. As I increase this to 100 Hz, we see a full cycle in the bottom and close to 3 cycles in the top. And further increasing this to 200 Hz, we see the pattern continue. Let me stop the simulation and change the target rate from 10 kilohertz to 20 kilohertz, and we'll see what that does to the CPU utilization, which right now is at 34.97%. Re-executing, loading the out file, the Launchpad is running, and we see we're consuming about 80% of CPU with double the rate, which makes sense. In the debug model, the target is executed at the time step value specified in the source model used to produce the C code. After compilation, the value sample rate Hertz in the target interface block will default to 1 over the time step value that was specified in the source model. There are 3 ways to control the target sample rate or update time. In the source model, by setting the time step value under System Properties. In the debug model, through the target interface block, by setting the sample rate in Hertz. And finally, in the debug model, but for target calculation models that contain a hierarchy of compound blocks, with the topmost block configured with the Include Communication Interface setting, any lower level compound block may be configured by setting its local time step value located under the compound block properties. This video has explained and demonstrated the use of the monitor buffer read and write blocks to capture high-speed data produced on the target and illustrated how to present the data in an oscilloscope-like format using the VisSim plot block with external trigger selection. 2 methods of monitor buffering triggering were explained. The variable frequency ramp 32 block, located under Diagrams, Toolbox, Fixed Point, was also introduced to create a repeating time signal used to create a sine waveform. This toolbox provides many useful models for embedded applications. Finally, 3 methods of specifying the target sample rate were also explained.